Welcome to today's course on best practices in software engineering. So in the course this afternoon, we're going to be going through a few topics which I consider to be absolutely essential if you're planning on writing software which is ever going to be used for anything more than a quick little test on your computer. If you're writing software to be shared with other people, or writing software which published research is going to be relying on, then the things we're going to go through in the course this afternoon, I feel, are the entry level requirements for being able to say, I feel like I'm doing my stuff correctly. Now, that's not to say if you're not doing these things that you don't know how to program, that you're doing a bad job, that you're failing in some way, but these things are the steps that you can take to make it to go from being a programmer or a coder into being a software engineer. They start giving you the context and the terminology and the tools to structure your code and take it to the next level. The three things we're going to be covering in the course today are documentation, starting off with talking about how you can document your code both at a small level, as well as pointing you towards some tools which can be used at a much higher level. Licensing, when you come to share your code with other people, licensing and thinking about how you license your code is very important. We'll be going through a section there and I'll be inviting questions if anyone has any queries about what they can do on that front. And then most of the second half of the course today is going to be focused on testing. So testing is a way of making sure that your code does what you think it does when you went about writing it. So we're moving through those topics, probably the first two in the first half and then testing in the second half. But before we go ahead and actually dive into them, let's go ahead and get things set up in a way that's going to allow us to follow through the notes in an easy way. So I've started up Jupyter Lab here. So I've launched Anaconda Navigator and launched Jupyter Lab. So I'm going to be using this tool to write my scripts, run my scripts, and I'm also going to be using the Python console, also known as IPython, in this session today. You're welcome to use whatever layout of software you wish to use, whether you're using something like VS Code, or PyCharm, or Sublime, or just the terminal with Vim or Emacs. All of those are completely fine. That said, if you're having any issues with those other technologies, we're going to be less able to help because we've designed this course around using Jupyter Lab, and that's what I'll be using on the screen. So if you have issues with those other tools, you can try and ask questions, but we're not going to be able to devote as much time to helping you because we need to make sure that the bulk of the class is moving on. So go ahead and start up whatever tool you're going to be using for writing your Python today. Like I said, I started up Jupyter Lab here. If you've been to any of our other courses in the last few months, you will recognize the interface is exactly the same thing as we've been doing in those previous sessions. The first thing I'm going to do, and this is, I suppose, a micro best practice, is traditionally we've just gone ahead and clicked on Notebook or clicked on Text File and started filling up our text editor file browser area on the left-hand side with a scattering of files all over the place, no real organization. And so the first thing we're going to do today is click on the new folder button, which is in the file browser on the left-hand side. It's the second button along the top. Or if you right-click in the white area on the left-hand side, there's a new folder pop-up that comes up as well. So we're going to make a folder to put all of our code into. It's going to make sure that everything's nice and well packaged. I'm sure that many of you do this kind of thing anyway, but it's good to start as we mean to go on and highlight the fact that organizing your code is one of the first and most basic best practices to adhere to. So I'm going to make a folder called best practices. I would if I could spell. And once I've made that folder, I'm going to double click on it to move inside it. So you see the path here now includes best practices, and you can see the folder that I'm sitting in is called temp/python/best practices. Yours might just be called best practices. Again, feel free to lay this out however you want. The tool that you're using may have a different way of doing that. I'll leave that up to you because you'll be the expert in your tool. But we're going to make sure that everything is inside this best practices folder. If you're using Jupyter Lab, make sure you do this before you launch notebooks and consoles. Otherwise, those notebooks and consoles might start pointing at the parent folder, not at the folder that we're in. There's ways to fix it, but it's easy just to start doing it the right way. So in the course today, we're going to be writing some Python scripts, we're going to be running some Python scripts, and we're going to be using the Python console as a way of investigating the code that we're writing and seeing some sort of experiments with how it's all working. So I'm going to create a few things. I'm going to make a text file or a text editor. By default, it makes one called untitled.txt. Of course, we'll be renaming that shortly, but for now, that's fine. We're also then going to click on the plus in the top left to make a new launcher, and we're going to launch a terminal. And then I'm going to drag this terminal over to the right-hand side. So you click and drag on the tab, and it ends up over here. By default, when you open a terminal in JupyterLab, it will be pointing at the parent directory, not in the best practices folder that we're currently sitting in. So make sure that when you open up the terminal, you type cd space best practices and then press enter. And on my terminal, it's showing up that I'm in the best practices folder. Yours may or may not display that same thing, but if you've done cd best practices, then it will all be working just fine. The last thing I'm going to do is create a new launcher again, and this time I'm going to launch a console, not a notebook, a console. Click on the Python 3 button, and I'm going to drag that so that it's in the top right. So I've kind of got a 3-pane thing going on with the editor on the left-hand side, the console at the top, and the the terminal at the bottom right. So just take a minute or so now to set up your stuff so it's laid out in a similar way to this. However you want to set it up is fine, but this is what I'll be sticking with for the course today. Take 30 seconds or so to set that up, and then we'll get on with the material. One thing I will say about setting these things up is I made sure that the terminal was in the best practice folder by doing cd best practices. It's worth checking that the console is also in the right area. So if you do %pwd, which stands for print working directory, i.e. print the directory that we're currently working in, and you run that with Shift Enter, it should print out the folder that ends in best practices as well. So that's a good way of checking that the two are in the same place. If it prints the thing without best practices on the end, then you can change directory with %cd best practices and then press enter. It won't work for me because I'm already in that folder. So if you're not in the right folder in the console, then change directory with cd. So Peter's asking what's the difference between !cd and %cd. It's a subtle difference. So in the console, % will always call the underlying operating system command that you follow the % sign. So you could do %echo to run the echo command, you could do %python to run the python command, and so %cd will change the directory underlying. Whereas %cd is telling the Jupyter kernel, the Python kernel inside the console window here, that it should start dealing with the stuff inside the directory you're moving into. I believe that in most cases, these two are going to be identical. However, if you're on an operating system which doesn't have a command called cd, then the latter will still work, whereas the first one won't. pwd, for example, is a Linux command, so we could do %pwd, and that would work fine. However, if you're on Windows, I don't know, but that one might not work because I don't think that pwd is necessarily a Windows command that you can run, whereas %pwd will always work because Jupyter and Python are kind of doing the conversion for you. We're going to jump into the first page of the notes now, so I'm going to, on my shared screen, scroll to the bottom. This whole first page of the notes is setting up Anaconda in the way that I did, including making the best practices folder, so make sure you've done that if you haven't already, laying out the windows, and finally moving into the folder with cd. So moving to the next page of the notes, we are on documentation. So for much of the examples here, I'm going to be working in the console, so I'm going to resize the window a little bit so we can see better what's going on. And we're going to see some of the tools that Python provides for writing and reading documentation when you're writing Python code. While this course is called Best Practices in Software Engineering, which is a very general title, which doesn't mention Python specifically, all the examples and all the stuff we're going through today is going to be using Python, because I feel that Python provides a really good environment for doing these best practices. That said, all of the concepts that we learn today are pretty much transferable to any modern programming language. You could do the same thing in R or Julia or Go or Rust or C++. You'll have trouble doing some of these things in very, very old languages. If you're still writing in Fortran 77, you might have trouble with some of the things we're doing. Or if you're using something like COBOL, then likewise, it doesn't have the same tooling around it. But any language that was designed since about 1990 will be supporting the kind of things that we're doing today. Because over the years, people have learnt how to design and write programming languages to help the users do things in the best way. Documentation is the first one. So long ago, people realized that you can't just write code, you have to document it. There's different types of documentation that come into play. There's documentation where you write a program and you want to explain to people how they can use your program. So you write a kind of a manual or a tutorial which explains people how to install your software, run the examples, and extract output from it. That's one kind of documentation which is really, really important to do, the tutorial or manual type documentation. The kind of documentation we're going to be focusing on today is the lower level documentation which is designed not for end users of your product, but for people who are going to be using the APIs and the software that you're writing as programmers. So if you're writing a function or a class or a module and you want other people to be able to use that function, class or module, this is the documentation which is going to help them understand how to use it. It's the same kind of documentation that you'll be using when you're going to docs.python.org and looking up how does the list.append function work. That kind of function level documentation. So first let's have a look at what Python can tell us about functions that are already built in. So if you type the name of any function into the console window and follow it with a question mark, and then run that cell with Shift-Enter, it will display onto the screen the documentation for that function. So you see here, it's telling us what the doc string is, blah, 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 blah. It's also telling us what the type of the thing that was in front of the question mark was. It is a built-in function or method. Largely, we can ignore this type thing because all the stuff we're going to be asking questions of are going to be functions or methods. The important stuff here is the thing inside the doc string. Now this doc string here is a bit of text which is written by usually the person who also wrote the function. It's probably not the case with the print function because the print function's been around such a long time. But in principle, when someone wrote this print function and decided how it was going to work, they would have alongside that written a doc string. Now these doc strings are written by humans to be understood by humans. You want to have a balance of jargon and technical language because jargon and technical language are good for being very precise in a technical environment. But balancing that against being human and explaining to people how it works, what to be careful about, and what's going on behind the scenes that you should be aware of. The normal way that split is done is the first line of the doc string is usually a short summary in a technically jargony kind of way of what the arguments to the function are. Here it tells us that it takes a value, it takes ... which the person writing this documentation has assumed you as a user understand to mean you can pass more than one value, just pass value, 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 keep on going, as well as a bunch of other arguments that it takes. Each of which it's giving us what the default of that argument is so that we know we don't have to pass it in, and if we don't, what it's going to be set to by default. So this first line here is usually a nice short summary of what the function does in its most sort of basic code-based sense. The next thing you'd usually have is a one-line short human description of what the function does. So here it says it prints the values, where values referring to value in the argument list above, to a stream, or to sys.stdout by default. So this is written for a human who understands terminology like stream and stdout, which isn't necessarily your very, very most beginner Python programmer, but by the time you've been doing it for a while, hopefully these terms are starting to make some sense. Particularly, I hope that you've come across the term stdout, which is referring to the standard out, which is where, by default, everything gets printed. It's the stuff that appears in your terminal down here. Following that, there's a short description of each of the arguments where a bit more description is needed. For example, sep is the string that gets inserted between values. So you see here it's kind of a combination of technical language and human language, and it's up to you as a documentation writer to think about the audience you're writing your documentation for. Is it for someone who has never programmed before and so prints the first function they use, and so you should make the documentation a little bit easy to read? Or are you writing some complex quantum function which calculates some kind of isosurface of some field, in which case you can get away with using more technical jargony language because the audience are technically inclined and understand the field in which you're working. So the first bit of advice I would give is think about the audience for the particular function that you're writing. I would argue that this print function, given that it's the first function that's ever talked to people in Python, should probably have a slightly nicer written bit of documentation. It should explain to someone who's never written Python before what's actually happening. This one kind of fails there, and quite a lot of Python docstrings fail when it comes to dumbing it down, as it were, for a new Python programmer. So always have that in the back of your mind when you're writing code. If you're, the other way we can get information about a function is instead of doing a question mark after it, we can also type the help function and put the name of the function inside there. That's going to give basically the same thing. We see it's printed out the same bit at the top, same summary, and then it's just been like indented and formatted a little bit differently. It's also wrapping weird on my screen, so I could do that and it would look a bit nicer, but I'm not going to go that far across. So we're going to start by writing our first function. It's a function we've used in some of our other courses. The details of what's in the function don't matter too much, but do feel free to ask if anything in there is not clear. We're going to write a function which, given two arrays, is going to add together the elements of those two arrays pairwise. It's going to add the first two elements of the two arrays into a result, the next two elements of the two arrays into a result, and so on and so on. And so we're going to call our function add arrays. The naming of your function is one of the first things that you come to when thinking about documentation. If you write a name of your function which describes what the function does, you can get away with a lot less documentation because people don't need to read the underlying text to understand what your function does. So think about ambiguity, think about your audience, and think about the context in which you're writing the function. I'm not trying to claim that add arrays is a perfect name for a function, given that it's adding together lists, but we can't have it all. Inside this, we are going to make an accumulation list. We're going to loop over the elements of x and the elements of y by zipping together x and y. We are going to append to z x lm, no, x lm plus y lm. For the purpose of this, the contents of this function aren't necessarily that important, but what we're going to be doing with the documentation of it is. So we've now written a function. I'm just going to double check that I've written this function correctly. I'm not seeing any obvious errors. If there is one, do shout out in chat. There we go, define a function. So if we want to find out information about this function, we can straight away go ahead and run add arrays and follow it by a question mark. We run that cell with Shift Enter. We see that it prints something out. By default, Python has tried to give us what information it can. So if you couldn't see cell 5 there and you didn't know what was going on inside it, and all you had was add arrays question mark, it's already told us what the signature of it is. So it's telling us that it takes 2 arguments. That's already a bit more useful than if we had nothing. The docstring, which before I was saying is the human written string, is currently no docstring. That's what we're going to be fixing in just a moment. It also tells us where that function was defined. It tells us it's in this thing here, and then it's in some temporary file, which isn't a real file. If you'd imported this function from a module, it would tell you here which module that function had been imported from. If we want to add a docstring to our function, I'm going to press up inside the console here twice so I get back to this. The way you do it is by making the very, very first line of code inside the function a string. Now it can be as simple as this is documentation, but the convention is with docstrings to use a special feature of Python, which are these triple quoted strings. So use 3 double quotes at the beginning and 3 double quotes at the end. The reason you do this is because it allows you to put new lines inside your string without having to worry about the other string getting broken up and stuff. If we run this, we can now do add arrays question mark, and it has the doc string now being set to what we just set it to. So have a go at that yourself now, defining that function, seeing what the doc string looks like without any doc string being set, then set the doc string to something, doesn't really matter what, and check that you see it coming through. That will make sure that we're all in the right place and we're all understanding this first step of the process. Just take a minute or so to do that, and then we'll carry on. Olivia asks, when I define the function a second time, does it override the first? So I defined this one, and then I defined this one. Yes, the second one overrides the first, so the first one's now completely gone. In the same way as doing a equals 5 and a equals 7, a is 7 after that cell has been finished. If the 5 has been completely forgotten about. It's the same idea. We had here defined our arrays function with a very, very poorly documented doc string. It doesn't describe anything about what the function does. The doc string here should be enough information for someone to work out exactly what your function does. All of the weird corner cases, all of the special cases. You could write half a page of text in there if you want to, if you have a complicated enough function. That said, if your doc string is starting to get very, very long because it's having to describe all of these complicated things about your function, that's often a sign that your function is too complicated. Just like there's a general rule that a function written should generally only take up a page of text at most, you shouldn't have to scroll around to read the whole of a function, I would say there's a similar rule about documentation for a function. If your documentation for a function is more than a page of text, as would be displayed in a web browser, then that function is probably too complicated and you should break it up into smaller parts. Having these sorts of rules of thumb are just suggestions, they're not absolute rules, but it's a good sort of thing to keep in the back of your mind as you're writing code, thinking this function is getting a bit hairy, I'm adding more and more if statements into it. How am I possibly going to describe to the user of this function what it does? I'm dreading writing the documentation because it's going to be complicated. That's a sign I should think a bit harder about how I should maybe split this function up into multiple parts. I'm giving you a couple of these sorts of rules of thumb throughout the course today, because while I could probably write a book about best practices, a lot of them come down to special cases in the situation that you're in. And so having hard and fast rules seldom work, but having bits of advice often are easier to implement when you actually come to writing your code and will be applicable to more of you. So I'm just going to press up on the keyboard twice so I get back to our documentation. So I'm going to delete this documentation here. And I'm going to do a proper job of writing the documentation. So the sorts of things that documentation usually want in it, if it's a function, I'm going to be using the functions as the example here, are number one, what arguments does it take? If they're going to call this function, what do they need to give to it? Now this is a few things you need for what arguments it takes. You need to know how many, what types they are, and if there's any restrictions on the kinds of values that are in there. For example, if you've got a function which is going to be dividing things, you might have a restriction which says none of the values that you pass in can be 0, because otherwise it's going to do a divide by 0. So while all other floating point numbers are fine, 0 isn't fine. So you want to describe how many arguments, what types they are, and if there are any restrictions. So let's do that. But the first thing we do is write a very, very short one-sentence summary of what goes on. Let's write adds together each pair of elements from the two lists. I'm sure I could write a better description of this function given time, and I'm sure if we work together we could come up with a nice pithy description. If anyone has any good one-sentence descriptions of what this function does, feel free to post them into the chat, and I'm happy to change mine to yours. So as I was saying, we need to tell it what arguments we take, and there's lots of different ways we could do this. We could say something like arguments are x and y, which should be lists. That's a perfectly reasonable way to describe what should be passed in and what restrictions they have on them. That said, while these docstrings are technically completely free text fields, you can write whatever you want, and you can write an essay or you could write a one sentence, there is some value in keeping them in a consistent format. There are, and we'll come to it at the end of this section, tools which will read your source code and can automatically generate web pages or PDFs or whatever from your documentation and will display your code and your documentation on a web page so that it looks nice. In order for those tools to understand what's inside your docstring, you need to write your docstring in a particular format. Unfortunately, since Python's been around a long time, over the years a whole bunch of different conventions have come along, so there's not just one. However, there is a particular convention which I particularly like, I find easy to read, and which I'm going to be following in this course. So unless you are working on software which has a different convention, I suggest using the convention that I'm going to show here. It is sometimes called the Google convention because I think it was originally established at Google for writing their Python code. And that is, we write a little block which contain our arguments. So we write args : and the next line we indent 4 spaces. And we're going to write a list of the arguments, one above the other. We give the name of the argument, and then in brackets the type of thing that it is, followed by a colon and a space, and then a description of what that argument is. And I'm going to write it's the first list to add, and we do the same thing with the second argument. The second list to add. So you want to make sure in here you have enough information for anyone who's using your function to know exactly what's going on. They see that this function takes x and y. They want to know what x is. They look here and they see that x, well, it's a list. They know they have to pass lists in, and it's the list that's going to be involved in the addition operation. Likewise, y, same situation because it's a nice, simple function. So that's covered our input arguments. We've covered what the arguments are, how many they are. Because we haven't said any of them are optional, these are all required arguments, what type they are, and how they're used. Once we've covered the inputs to our function, the next thing we need to make sure we always have in a docstring is any return values from the function. We need the inputs and we need the output. So here we do a second block, which is titled returns, and indent that. We tell it what type it's going to return, because they're obviously going to be writing something like a equals add arrays. So they need to know what type of variable a is going to be afterwards. They need to know, is it going to return a list? Is it going to return a Boolean? Is it going to return a numpy array, or something much more complicated? In this case, it's going to return a list, because, well, Z is a list. And so this is where we describe exactly what that variable is going to be holding. And I'm going to say it's the pairwise sums of x and, actually I'm going to use double y. So they know how x and y get involved in producing the return value, and these two things together are enough for someone to use the function. They could read the documentation, see what's going on, and find out exactly how this function is going to use their inputs and what they're going to be getting back. The final thing which I like to include in every single one of my docstrings is a short one-line example of how it can be used, because even reading documentation like this can be slightly heavy at times. You do have to read through all of the lines and understand what's going on. Often an example is the quickest and simplest way to explain to someone what your function does. And so we're going to add an examples section. It's plural because in principle you could have more than one example. And the convention here is to use 3 arrows or 3 greater than signs followed by a space to describe this is the input code that you would write. And we just give an example of add arrays being used. And we say if you pass it one list, which is 1, 2, 3, now let's do the same as in the documentation, 1, 4, 5, and that would be x, and a second list which is 4, 3, 5, then you should expect to get back whatever we put on this line, which should be 5, 7, and 10. So they can look at this and say, I know that I can import this function, and to check that I understand what's going on, I can just copy and paste this, run it, and check that I get the right output. If I get the right output, then I know the function's working. Then they can just start tweaking with the example you've given them, see how it affects the output, and learn how your function works sort of iteratively and exploratorily. That's a really nice thing to include. So I would always include an example in my documentation. One of the arguments against having examples in your documentation is that if you change how the function works, you have to update your example. Now, I would have two arguments against that being a bad thing. Firstly, if you have to change your example to accommodate how you changed your function, then all the people using your function are going to have to change their code as well. And so you should try not to do that because it's going to break their code. But secondly, if you accidentally change your code so that your example doesn't work anymore, there are things you can do to automatically run this line of code and compare it to the output and check that it's all working correctly. And we'll be covering that after the break in the testing section. With that, I think this is all we absolutely need for this, so I'm going to define that. And you notice here that there are a lot more lines of code of documentation than there are of actual Python code. That's not uncommon. I would say that it's not a bad thing to do because, well, A, describing things to humans is always going to be more verbose than describing something to a computer because humans have a wider range of ways of interpreting what you tell them. But secondly, explaining to people how your code is going to be used is absolutely essential if you actually want someone to use it. But let's check and see whether that actually worked. So we do add arrays question mark, run that, and we see it prints out the doc string is now all of the stuff that we could possibly need. Given the add arrays function, this here tells us everything we need to know how to use it. So take a minute now just to copy that in yourself. Just copy and pasting is fine. Copy it from the notes, type it out if you want to. Check that you're getting the documentation showing up, and then we'll move on to the next section. So there's a question there about what if the function returns a plot or an image? Should we include an example in the doc string? You still can. It's a little bit harder because your plot or image might change by 1 pixel and then your automatic checking might fail. So in that situation, I would think about what kind of promise I'm making from this function. I would try and make the body of that function as small as possible, and all of the code which actually does the job of constructing the plot into smaller sub-functions, so that all the stuff which munges the data, which makes sure the axes are there, which makes sure the ranges are set and the color bars set correctly, move those into other separate functions which return their own parts of the puzzle. Then your final function, which assembles it all together and returns the plot or the image, can then be easier to explain. Giving an example like this is still a good idea because someone reading the documentation will see what's going on. One of the best examples of this is the matplotlib gallery, which if you've been using Python for a while, you will have definitely come across. And you see here all of the different images which get shown if you run a particular piece of code. These aren't necessarily running a function, but running a piece of code. And if you look at them, you see the code at the bottom and the example plot at the top. And when they generate this web page, they generate the picture at the top by running the code at the bottom. This is how this web page is generated. And so while it won't be necessarily automatically checked, it's still automatically generated, which is a very, very nice thing to have to make sure that everything's kept in sync. Hopefully you all had a chance now to stick that in there and make sure that's working. So I would make sure you get in the habit of always writing a doc string for every single function you write. It seems onerous at first, but it's a really good way of getting down on paper exactly what this function is doing. If you can't summarize what your function does in one sentence, it's probably too complicated. If your documentation list of things takes up multiple pages, your function's probably too complicated. These are really good ways of describing how your function should be constructed as you're going along and thinking about what you're inflicting on the users of your function as you go. So we've covered here functions and how you document functions, and that's something that you should absolutely make sure you always do. Every function, big or small, give it a doc string. The second thing you often want to do is assemble your functions together into modules. So I'm going to make a file over here. I'm going to rename this file to arrays.py. It's turning it into a module, and I'm just going to copy and paste this function that we just defined into there, and I'm going to rejig this window a bit. If you get stuff going over multiple lines like this, sometimes you can just kind of manually reformat it a bit. Your screens probably aren't wrapping around as much as mine are because I've made my font big so that you can read it. So we can now save this. If we imported this module and asked questions of it, we would see the documentation for that function showing up exactly as we did when we defined it in the console. When we documented our function, we made sure that the first thing in the function was the docstring. We can apply that same logic to the module as a whole. If we make sure that the first thing in our module is a docstring, then that module is going to be documented by said string. So we do the same thing, 3 quotes and 3 quotes. JupyterLab kind of helpfully does both for us. It gets in the way more than not, but it's trying to help. And we want to write in here a description of what this module as a whole does. We can imagine we're going to have functions called add arrays as well as one called subtract arrays. We're going to be coming to that a little bit later. So let's describe our module by writing this module contains functions for manipulating and combining Python lists. 4. We can now save that, go over to our console and import it. Because we are in the same directory, this import should work. This is inside the best practice folder. We are in the best practice folder, so we can do import arrays. That means we can do arrays ? And it's going to print out documentation for the whole module, which is a nice thing to be able to do, and tells us that this thing is a module, and the docstring here describes what's going on inside. If you do it with a help function instead, you get a lot more information. At least you certainly used to. Yeah, it prints out loads. So here I've typed help arrays. So it's printed out what it's going to show me. It's told me it's a module, the description of the module, but then it's also gone and printed out all of the functions in the module along with their docstrings. So to get a short summary overview of a whole module, doing help on that module name is a nice shorthand way of doing that. If you do import arrays and arrays ? Doesn't print out the docstring, first thing to make sure is that you've saved your arrays file over here. So make sure there's not a black dot where the cross sign is. And if that still doesn't work, then what you need to do is right click in the console area, choose restart kernel and choose restart, and then re-import your module. The reason you have to do that is because if you import your module before you've added stuff in and then re-import it, the re-import does nothing. It just defaults back to however it was before. So if you're having issues with changes not showing up when importing modules, right click and choose restart kernel. Then that should work. Take a minute now to copy the code into a module, add in a docstring at the top of the module, import it into the console and check that everything's working. So there's a question from Mary there in the chat. What should you include in the docstring of classes with multiple functions inside? Or classes which are variations of other classes? Should you list each function in the class docstring and then do the function docstrings as normal? So when you're writing a class, the first thing to bear in mind is that a class shouldn't just be a bundle of functions assembled together. A class should be an abstraction of a concept in your code. It should be representing some kind of abstract noun of your code. And so the docstring of your class should do 2 things. Firstly, it should describe what that abstraction you're making is, what that class represents, what objects of that class are going to be holding. And secondly, you want to include more general information about how the various functions in that class interact with each other. So in the class documentation, you would often have a more general section describing how you construct pieces of that class, if you call it with some arguments or other arguments, how the resulting objects vary, if you call functions on it, how that changes stuff. So you might often write for a class a bit more explanation of how things work. I would still apply the same try not to make it more than a page if you can rule, because a class which is too complicated is going to be hard to use. But it is okay to kind of get a bit wordy and a bit kind of explanatory when you're documenting a class. Each of the functions inside that class I would still document in this same way. So I'd keep each function as a self-contained unit, which only depend on the arguments that are passed in and the state of the class. And keep the class documentation being how those functions relate to each other outside of their own little world. I do recommend having a look at the Python documentation. So if you look at docs.python.org and we go to library reference, because this is where all the functions are defined, and we just choose one at random, text wrap. So here we have the official Python documentation. The module documentation is this little paragraph at the top describing in general what this module does. And then each of the functions have got their own little bit of code. Now there aren't any... Oh, there's a class here. Okay. So each of these functions got their own bit of class, their own bit of explanation. For the class text wrapper, we see the documentation for the class is all of this stuff here. It's these, well, the general documentation is this stuff up here. Then it's describing the things that get passed to the constructor, or things that you can get out of it as attributes. This does go on a bit. My font's quite big, so it might fit on one page for you. But these are basically different pieces of data that you can get from it. So this class doesn't have functions. You could almost think of each of these attributes as being the equivalent of a function. So as long as you keep each attribute description short, keep this bit here in one page, you're going to be okay. Every class is going to be different though, so you do have to just apply a little bit of how I think this should work in this case. No one's going to say that you've done it wrong if you're doing it in your own way. As long as you're explaining to the user how it should be used, you're doing a great job. If you write any documentation at all for your classes or functions, you're already doing better than about half of the researchers at the university. So you're already in that elite class of people who are doing it the right way. The other thing I would say about documentation when you've got questions like that is it's really, really useful if you have people in your research group who you can talk to about these things. Doing kind of peer review of your code and documentation is just as important as peer review of research papers at the end of the day. Having someone else who you can show your code and documentation to and ask them to spend a few minutes trying to call that function and report back to you with any errors, either them emailing you back or you, even better, watching over their shoulder while they use it, is going to teach you a lot about how your function can be misused, since a good rule of thumb is good code is hard to use badly. You want to make it hard to use wrong and easy to use well. So having someone else who can review your documentation or code is a really, really valuable thing to have. So the last few things I want to talk about documentation are firstly the workflow that you go through. And the workflow that I'm going to describe is basically the opposite of what I just did, because I wanted to start from one place and move my way along. There is a style of development called documentation-driven development. And that is, we pretend we don't have that at a raise function. We start off with def something, because I don't know what my function is going to be called yet, and it's going to take some argument. I don't know what they're going to take yet, and I fill it with a pass, which means don't do anything. And apart from that, the first thing I do is write the documentation. I sit down and think, what is this class going to do? Or what is this function going to do? What is this module going to do? And I start by writing to the user how this function is going to be used. So I write something like subtract two lists from each other. Subtract, not subtract. At that point, I've worked out what the function kind of does in one sentence summary. I know it's got two lists, so okay, I'm going to give it two arguments. At this point, I think, all right, what should I call my function? I'm going to call it subtract arrays, only for consistency. And then I think, okay, so I need to document my arguments. I've got X and I've got Y, and it returns something else. And I pretty much write my entire documentation string before I ever go about writing the code that goes inside. Once I've got the description of how the function works, what the inputs are, how the return value is constructed, an example of how it's being used, I can then go ahead and write my code to make sure I'm fulfilling the promise that I made when I wrote the documentation for the user. The reason this way round is often better is that it forces you to think about what problem you're actually trying to solve. Writing things in human language for other humans as a human is often the easiest way to get your thoughts out. Now, if you write it in a doc string in a piece of code, or whether you get a piece of paper out and write it down there, or if you open up a Word document and write it in there, none of those are necessarily any better than the others. They're all perfectly valid ways to do it. But by putting it directly into the code here, you've already got your documentation written. That way you don't have to worry about, oh, I'm not going to get around to writing the documentation. You've built it into your development process. Then when you're writing your code, you check that you keep writing your code until your example works. Once your example works, you think, okay, good. I've finished writing this function now, and you can move on. And that's a really helpful way of structuring the development of your code, making sure you actually do the documentation, as well as before you even write any code, thinking, how complex is this function? Is it going to take me days and days to document and therefore it's going to be hard to explain and therefore hard to use and write? Or can I summarize it in one sentence and therefore it's only going to be 10 lines of code? And so it's going to be only an hour, or I've taken a week to write 10 lines of code before, or a week. So doing it this way around can sometimes be beneficial. I'm not going to insist that everyone always does it this way around because every situation is different. But this documentation-driven development method can often be beneficial. We'll be seeing another example of something-driven development when we get to the testing section later on, which you might have come across. The last thing I wanted to cover in the documentation section was web pages. So we're using Python here to explore these ideas. And as I said, all other languages have the same kind of concepts in them. And that extends to generating web page documentation for your software. If you want to write software to be used by other people, you need to advertise and give them a place they can go to find out how it works. And so in Python, there's a tool called Sphinx. Other languages have similar tools. If you've ever written C++, you're bound to have come across Doctests, for example. But all languages have a similar kind of idea. I'm not going to go through this page here because it gets a bit fiddly and it's hard to debug, especially when we're online like this. But I do recommend you coming back to this appendix after the session and having a go yourself. But in summary, if you write your doc strings in that way that I showed you in the Google style, you install Sphinx, just a Python package, so it's easy to install. You then point it at your source code and it will generate a web page which looks something like this. If you then point it at the module that you care about and tell it what you're looking for, it will generate a page that looks something like this. So it's the documentation of the whole module. You see the first line up there is the module doc string that we wrote. Then it's done the add arrays documentation as well. And you see, because we use that particular format with the args and examples, etc., it has correctly laid out the parameters as a list, put the things in brackets, and it's made the example at the bottom look like Python code. So it all starts looking nice. Having a web page like this for any software which you're publishing out into the wild immediately makes you look like you know what you're doing. It makes you look professional. And even if you don't necessarily feel like a professional programmer, as soon as you're doing things like this, you are immediately starting to put on that hat without realizing it. And as soon as you get in the habit of doing these things, you will just accidentally become a professional programmer without realizing it all along. So we've got about half an hour or so until the break, and hopefully we can get through the next chapter and maybe even start on testing before then. But before we get to testing, I wanted to talk about licensing. Now, this is something which I find a bit easy to geek out on and start going on at people about. And that's because I come from a school of software development which is very heavily involved in open source code. So the idea that you're writing software which is shared and freely available and given to people and all this kind of thing. And the very basis of all of that is copyright and licensing. And so I really start caring about these things and start going on about them a lot. So hopefully I'll be able to keep this short. But any questions along the way, do feel free to pipe up in the chat and let me know. But the things that you need to be aware of, if you're writing research code or writing code for research or any kind of code that you want to share with people, you will often want to share that code with other people. And I'm going to come on to later about considerations about when you can and can't and so on. But if you ever want to share your code with anyone else, and this isn't necessarily restricted to publishing it as an official package on GitHub or on the Python package interface or anything like this. This is just if you want to give your code to someone else, you need to be aware of what the law says that they can and can't do with the code that you've given them. And this all comes down to the Berne Convention, which was signed during Queen Victoria's reign, so it's been around quite a while now. But the summary of what that international agreement says, and it was signed by most of the countries of the world, or has been since, is that every single piece of work which is potentially viewed as an artistic work or a work of effort is automatically copyrighted. And now what copyright means is that if you create something, you have the exclusive right to produce copies of that work. So no one else, even if you give them it, they are not allowed to make a copy of the thing that you made. If you write a book and give someone a copy of that book, they're not allowed to start photocopying it and handing it out. That's what the word copyright means. It means the right to make copies is held by the person who made the work. And that applies to things like books and artworks and music, and it applies to software, or at least it applies to source code. I think it does apply to software as well. And that means if you write a piece of software to do a bit of research, and you email it to a colleague because they're asking about how it works and so on, you need to be aware of what they're allowed to do with it. Now, by default, they're almost allowed to do nothing with it at all. They can't make copies, they can't send it to anyone else. So you need to be very explicit about what you're allowing people to do with the software that you're handing around to them. And since this software stuff is all so restrictive, there came a world of software licensing to kind of establish what the bounds were for any particular thing that you create. And from that world came the open source movement. So in the 1980s, when people were still handing around software on 5.5-inch floppy disks and so on at universities, people started to realise that this was going to be a problem, and so they wanted to establish a legal framework to describe what people would do with their code. And because the people who were designing this system cared about freedom, and they were sort of ex-hippies, the most of them, they wanted to make things as open and shareable as possible. And this is where the open source movement comes from. Sometimes it's called free software, sometimes it's called open source. As far as we're concerned today, they are equivalent terms. There are differences, but I won't go into them. And from that world of making things nice and shared and open, and having these open source pieces of software, come things that we use today. For example, I'm running Linux on my laptop that I'm sharing the screen from today. Linux is completely free and open source, anyone can get access to it, and anyone can look at the source code and see what's going on. The Python programming language is completely free and open source. There's no restrictions on it, not like MATLAB or Mathematica where you have to buy a license. It is free for you to do whatever you want with, as long as you follow the terms of the license that it's shared with you. Also, things like Firefox and Wikipedia and VLC are all free and open source. They are freely available and you can do what you want with them and you can see what's going on inside. And over the years, people have kind of established what the common ideas and things that they should be allowed to do with software are. And one of the common ways that these are described are with the 4 freedoms. And these are worth being aware of because it gives you a sense of what you're allowing people to do if you choose to make your code open source. So the first is the freedom to run the program as you wish for any purpose. And that means you can't say to someone, you can use this, but you can't use it for commercial purposes. Or you can't use it to write a competing paper against my research, for example. It has to be free for any purpose whatsoever. Secondly, they need to be able to see how it works. This is usually, they've got to be able to see the source code. You've got to give them the source code, not just the finished, compiled executable. Thirdly, they need to be able to redistribute copies. Now, this is where the copyright thing comes in. You are giving them the right to copy your work, as long as the thing that they hand on has the same conditions and constraints as the thing you gave them. So they have to pass on those same freedoms on the whole. So free software works by working within the realm of copyright law, but applying these different sort of freedoms on top of it by relaxing the constraints in various ways as they see fit. So for example, even though something like Chrome is free, you can get access to it and download it, it is not free software or open source software. You can't see what's going on underneath it. The executable you download, you're not allowed to share around with people, for example, because Google say that we are the ones who are allowed to distribute it. It is not freely available. Also, things like Microsoft Word, they are closed source. You can't see what's going on inside. So if there's a bug or a security error, you've got no way of knowing. Now, as a researcher, I'm currently exclusively funded by public money. That's taxpayers' money. That's your money and your family's money and your friends' money. And I feel that because of that, I have a moral duty to take whatever I'm creating that's being paid for by them and allow them to have access to it. And the way I do that is by making every single piece of software I write completely free and open source. The documentation that we're going through today, the course notes, these are all freely openly licensed. All of the source code snippets are freely and openly licensed. And all the software that I write as part of my research are freely available for anyone in the world to get access to. It allows other researchers around the world to build on my stuff I've been doing. And it also gives me a public profile where people can see what I've done and show that my work is useful to people because other people are using it. And that's a really valuable thing to have when you're trying to build up a portfolio. It's not just about papers. Showing that your work is valuable to other people also has value. I always have the opinion that everything I make should be open source, but that's not necessarily always going to be the case. So let's say that I have convinced you that you want to make your next bit of software you're writing open source. You do have to think about a few things. So firstly, if you are working together with someone on a bit of software, then you both share the copyright for the final work effectively. And so if you want to write or you want to apply a license to that bit of software, which says people can share it around and use it for whatever they want, both of the people there need to both give permission for that. So every co-author and copyright holder all have to give permission for a piece of work to be relicensed. The easiest way to do that is to make it open source from the very beginning, and then from that point on, it can't be un-open sourced effectively, and so it makes it easy to track down. If it's something that was written 20 years ago and some of the copyright holders have retired and you can't contact them, it's going to be a lot harder. So the earlier you do this stuff is going to make things a lot easier. The other consideration, this is particularly happens at universities, is if there's an industrial collaboration. Maybe Rolls-Royce is paying for the research that you're doing, and so they don't want the software to be open because they think it's going to destroy their competitive advantage. They have as much say as you do. They have paid for you to do the work. It's a work for hire. They have a right and a say over the copyright and the licensing. So you have to involve them in any conversation about what's going on. So make sure you've got the permission, explicit permission, of all of the people involved who might potentially have copyright. If you have any questions about who has copyright and who doesn't, that's the point to go and talk to a lawyer, not to me, because I won't be able to give you advice on that. But the university can help in some of those situations as well. So if in doubt, talk to your collaborators, if you're a PhD student, talk to your supervisor. If you're a postdoc or a PI, talk to your colleagues and find out what's possible. Or talk to us and we'll see what we can do. The other time that people don't want to make their code open source is very, very common at universities, and that is they're basically a bit embarrassed by it, or they think that it's going to be stolen and they're going to lose their research advantage. They've written some clever algorithm and they want to be able to publish papers on it for the next 40 years without anyone finding out what's going on. One solution to the whole stealing the code and publishing a competing paper is to make it open source but don't share it until you publish a paper, and then you can share it out there and say, here's the paper that has my science results in, here's the code that produced them, why don't you go away and see if you can reproduce it? And if you can, that makes my research more valid because other people are showing that it's correct. That's a really, really helpful thing to have, and a lot more funding councils, in the UK at least, are starting to really encourage people to make their software open source so that it can be reproduced, so that other people can check whether the research is right or not. Because if it turns out it's not right, keeping your software hidden doesn't magically make your research correct. It just means that you're doing science wrong. lying and saying, I'm not going to investigate this potential source of error because I think that there might be an error there and I don't want people to find it, is bad science. By sharing your code openly, allowing other people to work on it and help you write the software is going to make the software better. It's going to make it less likely to have bugs. And so you're not going to have to retract a paper later on when someone does find a mistake in your paper because they found a bug in your software when you finally do release it, or they try and reproduce it independently and find that you did something wrong. There's lots and lots of good examples of people having to retract papers because of software bugs. And most of the time it's because they weren't sharing the code openly, weren't collaborating, and were trying to keep their competitive advantage without realizing that they didn't have one because the code was incorrect. And that's part of what this course we're going through today is showing you how you can both share and test your code to make sure you're not making these same mistakes. So, hopefully now again, I've continued to make you feel like maybe you should be open sourcing some of your code if you were slightly on the fence before. As you can see, I do care about this stuff and I can talk about it for hours and hours, so never corner me because I'll escape by boring you with licensing talk. Let's say I have convinced you. Now we need to think about what the actual physical steps are to make it so that people can use your code in the open source situation. So the first thing you need to do is choose a license. Remember I said that by default everything is copyrighted and you can choose to relax that copyright in various ways. There's lots of documents already written by lawyers who know how to write legal documents to relax the constraints in a way that's appropriate for what you want to do. So there's lots and lots of different ways that you can license your code, all of which are open source, but they have different constraints and freedoms that you give to people. Simplest way to do this is to go to a website like choosealicense.com, and it gives you 3 simple options. Firstly, I need to work in a community. This is if you're already working with people, you should choose a license which is compatible with them, or just use a license which is already on the work that you're using. So that's the easiest one, just use what your colleagues are using. That's nice and simple. But apart from that, if you've got a new piece of software which you want to decide to make open source, you have a main choice between it being permissive, and that is you relax as many of the constraints of copyright as you can. You basically say to people, you have the right to do whatever you want with this code. You can make it commercial, you can keep it private, you can change it, you can mess it around, you can give it to people, but that's pretty much it. You can do whatever you want with it. At most, it's usually you can do all those things as long as you keep giving me credit for the piece of software, but that's usually the only real constraint, is that the authorship should be maintained. On the other side are things like the GPL, which is what Linux is developed under, and this relaxes fewer of the constraints, with the idea being that if you write some software, release it under the GPL license, if someone uses that software that you've written in their product, they have to also make their product open source. With the idea being that the GPL is kind of viral in the sense of it spreads the open sourceness throughout the world. So more people are encouraged to make their software open source if they want to use other open source software. So this kind of comes down to a philosophical difference between the two. I use one or the other depending on what kind of software I'm writing and my mood that particular day. All of the stuff that we've done in the course today, where it is copyrightable, is released under the MIT license, because that means you can use it freely as long as you mention somewhere in there that it was a bit of the code was written by me. You can make it code source, you can not publish it at all. That's all completely fine. But using one of these, you click on MIT license and it gives you the copyright text. So you clear that copyright text, and the job you basically then do is take that and put it inside your source code repository. So if you've got it on GitHub, you put this in a file called license.txt. You replace the year with the year and the full name with your name. And then this here is the legal document in its entirety, which lets people know what they can and can't do with your software. Once you've got that in there, you have open sourced your code, but you still need to actually share it with people. So the easiest way to share your code is on somewhere like GitHub or GitLab. So if we look at, for example, the GitHub page for PyTest, which is a product we're going to be using shortly, we see up here, well, we see down here, there is a license file. We can also get to it by clicking on this bar at the top. There's a thing there that says MIT in the top right. which if we click on that, it's telling us, well, it's under the MIT license, named after the university, and it gives a short summary at the top about what that license means. People can use it for commercial use, they can modify it, they can distribute it, they can use it for private use. Importantly, most of these licenses also have a liability waiver and a reduction of warranty. That means that even if I run PyTest on my computer and it breaks it, they are not liable for any damages performed. Likewise, if the software stops working, they don't have to fix it for me. They are waiving that restriction, that legal thing that might be there. So licenses have two purposes: waiving copyright to certain degrees and reducing liabilities and warranties, because you don't want to be stuck looking after something for a long time. Peter's asking, can I change a license over time? If you are the sole copyright owner over a piece of software, you can release versions 1 and 2 under the MIT license, then release version 3 under the GPL, and then release version 4 completely on open source and keep it private if you so wish. The thing to remember is that versions 1 and 2 will remain under the original license. You can't revert a license. They are unrevocable on the whole. But you can choose to change it later on. So if you start closed source, you can later on release a version which is open source if you so wish. As long as for each stage of that process, you establish what the license under that code is with any collaborators. Matt's asking, is there a stipulation on differences between versions? So version isn't a term that's recognised under copyright law. What you're talking about is effectively a work. So if you release a given work which you decide to label as being version 1, that work has that license from then and forever. If you release another version later on, if anything has changed in there which is significant, then that will be treated as either a new work or at least a derivative work, in which case you would be able to potentially license it differently. It's even possible to have a particular work licensed under multiple licenses. You can, for example, have some software which is commercial and open source. So it's quite common to apply a GPL license to your software, which is quite restrictive, but nonetheless completely open source. But then offer to sell to companies a special bespoke license which allows that company to use it under non-open source conditions. That way you get a revenue stream coming in from selling licenses to companies, so they can use it inside their products without having to make their software open source. Meanwhile, allowing the software itself to be freely available for other people who want to use it in open source software without any restrictions beyond that. So David asks, what aspects of code are copyrighted? Is it the literal text of the code? If someone were to change the variable names or other aspects which don't change how code functions and pass it off as their own code, would that breach copyright? Now, I can't give you legal advice on this, David, because this is exactly the sort of thing that multi-million-pound lawsuits are being fought over between Oracle and Google, for example, over the copyright in Java. So it does get very, very gnarly. There is, in general, these things in general can only be solved in court by a judge, and so there's not necessarily a solid answer. There is a limit on what has to be significant. So, for example, if you contribute to someone's software, you would have to make a significant change to it for that to be deemed as you having any level of copyright over that code. And to avoid that, the general rule is every change, no matter how small, is automatically significant, because that's the safest way to play it. If someone to change the variable names, other aspects, and try to pass it off as their own, that would, by definition, be a derivative work from what you created. They have copied your code, and even if they've changed it, it is still technically tainted by your original ownership on that code. Even if they took your code, changed it so much that you couldn't recognize it anymore, still legally it would be a derivative work from what you made, and so they'd have to abide by your copyright licenses. However, proving to a judge that they copied your code would be more difficult. So with many of these things, it comes down to A, playing it safe, and B, I can't give you an answer because only a judge can make that kind of decision, or a court at least of some kind. So the safest thing to do is to play it safe. If you think that someone is taking your code and trying to pass it off, that's the time to contact a lawyer and see what their opinion is, because I can't give you any advice, but I would say that I would expect that you would have a case in that situation that they were indeed violating your copyright. and violating the license you've given it to them under. Okay, so let's get started with the second half of the course today. We're going to be going through testing. So testing is one of my favourite topics to talk about when it comes to software. Anyone who's hung around me in a professional context will have heard me go on about testing several times a week, because I think it's one of the most important and one of the most useful tools you can have as a software developer. When I started writing software, however long ago, 20 years ago or something, I didn't know about testing. I didn't bother with testing. It took 10 years before I really bothered sort of learning about what it was, and another several years before I actually convinced myself that it was actually worthwhile and a good idea. It was a long, slow process, but now looking back, I wish that I'd got in on it sooner, because I really do see the value in it, and it makes my code so much better, and it makes the software development experience so much better for me now. At its core, testing is how you make sure that your software does what you thought you were writing it to do. If you don't test your software, you don't know if it works, so it may as well not work. If someone shows me a piece of software and say, hey, look, I've got this bit of software, it solves this problem, the first thing I'm going to ask them is, how do you know that it solves that problem? Have you checked? Now, them having checked can be as simple as running a couple of manual examples, and that's going to convince me a bit. But the more different tests and the more depth of testing they've done to it, the more and more convinced I'm going to be. And I apply that same logic to research when I see it being published. If someone publishes something they've discovered, I'm going to ask the question, as any reviewer would, how do you know that your discovery is true? Have you checked? Have you checked this thing? Have you checked that thing? Have you looked at your errors? Have you looked at your modelling uncertainties? If there's software involved in the process of producing that research, I'm going to be asking the same question going down that chain. I'm going to be saying, have you checked that your software is doing the correct thing? Is it modelling what you think it is? Is it giving you the uncertainties you expect it to? If they haven't checked those things, I'm not going to trust the research that's built on top of it. So throughout the rest of the session, we're going to be learning about how you can test, and I'm going to try and convince you why you should test. We're also going to be covering when you should test, because that's an important question which is worth thinking about as you're going through. So maybe you're already doing lots and lots of formal testing of your code, in which case some of the things we're going to go through in this section might be something you've covered before, or we might be using tools which you haven't seen before, in which case hopefully I'll be making your life a little bit easier. But at the very least, I expect that all of you, when you're writing code, have at least been doing some kind of manual checking. You write a script with a couple of functions in it, and it loads some modules from NumPy or from Pandas, and you put your input file in, and you check it runs, and you look at the graph, and you say, okay, that's worked. I've got a graph, and it's got a lump in the place that I expected it to. Or maybe you're doing a little bit better, and you're checking it with a couple of different known inputs. It's like a mathematical thing of some kind, and you're checking that the outputs look like they're in the right kind of range, and that's making you more and more convinced that you've done the right thing. But you really, really can't be sure that it's doing the right thing. You can't be sure there's not a subtle bug that's slipping through, that means some data's being missed out, that means you're dividing by a number that's using the wrong units. And even if you did manage to work out there was a bug, it's going to be hard for you to work out where that bug is happening in your code, because you've got one big monolith of code such as one long script. So to be confident that your code is doing the right thing, you need a suite of tests. You need multiple tests covering different aspects of your code, covering different kinds of things in your code, and checking that they are all giving you back the answer that you expect. A test suite is also useful because if you have lots of small tests testing little chunks of your code, if just one test fails, you know that the problem is likely isolated inside that small part of code that it was testing, whereas the rest of your software is continuing to work correctly. And so the general idea in testing that it's useful to have what are called unit tests. Tests which check that the smallest units of your program are performing as you want them to. In Python, this small unit is often a function, though you usually want to test classes as well. But a function is generally the smallest bit of code that you can test in isolation. So we're going to go through a little exercise now to see how you can apply this to the example we had before. And then we're going to build that up, making more and more formal tools and seeing how we can test more and more without having to spend too much time doing it and without having to write too much code. So I'm going to delete this subtract arrays function. In a little bit, I'm going to be asking you to write that subtract arrays function, but for now, let's just delete it and stick with our arrays.py file. I'm going to make this a little bit bigger down here because we're going to be working in the terminal for a while. As well as our arrays.py file, I'm going to make a second file by clicking on the plus up here, text file, and I'm going to rename this file to arrays.py. So I'm giving it the same name as the file which contains our functions, but I'm just prefixing it with test underscore, so I remember that this is the code that's going to be checking that the other code works. I tend to follow the model of having one file, which is my module, which contains the code that does all the work and has all the functionality inside it. And I have my tests in a separate file, which sits usually next to it in the same folder, which tests that that code works correctly. That means that the two things aren't being kind of mixed together too much. I've got the code just in isolation, which does the work, and I've got the tests in isolation, which check the other ones. So let's start by checking whether our add arrays function works as it promises to. We've written documentation which says it works in a certain way. We haven't actually checked yet. Of course, you would expect that I've checked before starting this session, but never assume. From arrays, import add arrays. So we're going to go to the file that's next to us and import the add arrays function. Then for each thing that I'm going to test, I'm going to write a little function which contains the code which performs the test. I'm going to put this inside a function so that it's bunched up in one little place. It doesn't need to be inside a function, but it will make our life easier in a little bit. I'm going to call this test add arrays. This function isn't going to take any arguments because it doesn't need to, because it's all going to be self-contained. The nice thing about tests is having them being self-contained on the whole. We're going to just make some example data, 1, 2, and 3, b equals 4, 5, and 6. So a test is usually best if it contains what the inputs to your thing that you're testing are, and also what the expected output of that test is going to be. We say, if we put these inputs in, what do we expect to get back? And when working out what you expect, the best way to do it isn't to run the function and copy it in. It's to think about what your function does. You should be able to read the documentation and work it out just by looking at what the string says and doing the maths manually. Or if it's something more complicated, you get out a bit of paper and if it's a mathematical operation, you do the maths on a piece of paper, for example. At the very least, it's worth thinking through what the expected output would be. In our case, it's 1 plus 4, which is 5, 2 plus 5, which is 7, and 3 plus 6, which is 9. Once we've defined our inputs and our expected outputs, we go ahead and work out what our actual output is going to be by calling the function itself. We pass in our two inputs, and what we want to happen is for expect and output to have the same value. So let's check if that's true. If output is equal to expect, then let's print OK. Otherwise, let's print broken. Now, at the moment, we've defined a function, but we haven't called it. So let's go ahead and actually call our function as well. At this point, we should be able to, because we are inside our best practice folder. On Linux or Mac, you can type ls. On Windows, you can type dir. And you should see the arrays.py and the test arrays.py files sitting inside there. We can run our test script. We're not going to run our module. We're going to run our test script just by itself as a script. And we run it, and we see what happens, and it prints out OK. So we know that our function is giving back the expected outputs for the arguments that we're putting in. That means that we are now more confident that our test works. We've now also written in a piece of code what our test is. We've codified it. We've written it down somewhere. And that means that this file can live here forever. we can make changes to how our code works. And as long as when we run Python test_arrays.py we get OK printed out, we therefore know that our code still works. Or at least it still works given these conditions. So we're already helping ourselves by slightly automating and formalizing the testing that we're doing. So take a minute now to write this test_arrays.py file and run it on the terminal and check that you're happy with the output. Then try changing the inputs or the outputs to break our test so you get broken printed out, and make sure you understand why that's happening. And then we'll jump on to the next section. I'll just give you a minute or so to work on that, and then we'll carry on. So hopefully you've all got that working now. You've got your OK being printed out, and to a demonstration, if I change this 9 into a 999 and run it again, I get printed out broken, because no longer does expect and output match each other. So this is working fine. We've got a good test here, which is checking whether our code is working or not. But imagine we wanted to add a second test, test add arrays 2, and this one is doing something different. It's adding zeros at the end, let's say. But this test is failing because we forgot to update it correctly. And we've got our 2 tests being run here. If we now run this in the terminal, we get OK broken printed out, which is useful. We know that one of our tests is broken and one of them's working. But to work out which is which, we have to look at the order of these, go over here, work out which one is the broken one, then refer back to here and find it, and then work out what's going on. It's not giving us very useful output. And the reason that's happening is because as soon as one test is breaking, it's just carrying on and doing the other one. So if we switch these two round, it would now print the other way round, and it's carrying on after the failing test, but not telling us what went wrong. So a thing that we can do to make it so that it gives us information about where the broken test is happening is to, instead of using this if-else block and just printing stuff to the screen, to instead use features built into Python which check for conditions being true or not and raise an error in the situation that they're not. So just going to have a quick diversion in the console for a second. So you're hopefully comfortable with statements like 5 is equal to 5, and it gives you back true, and 5 is equal to 6, and it gives you back false. Python has built into it a keyword called assert, which is going to assert that something is true. So if we do assert 5 is equal to 5, this is going to check the value of 5 is equal to 5, and if it's true, like it is, nothing happens. It just carries on and says, that's fine, you've asserted that's true, that assertion is correct. However, if you try and assert something which is false, it will then raise an assertion error. And so we can use this functionality here in our tests to, if the output and expect are matching, to just carry on and everything's okay. Or if there's an error, to explicitly tell us what's happened as well as where it happened. And that's a useful thing to have. So we can just delete those lines, turn the if into assert. And now when we run our code, get rid of the colon. Now when we run our code, nothing gets printed out. So in this situation, because nothing has gone wrong, it's done that classic Linux thing of saying nothing because nothing's gone wrong, and so you don't need to know anything more. Everything's great. However, if we change this into something which is broken and we run our code, it explicitly tells us that there was an error. It happened on this line and in this function here. So that means as soon as we get this happening, we can immediately look in our code and we know that it's happening in this function over here, and we can work out what's going on. So by using the assert statement, we've now got an explicit printing of where the error is happening. However, we've kind of reintroduced a problem, and that is if we go back to our situation where we have our 2 tests, and the first one fails but the second one is passing, it's going to run the first test. That's going to raise an exception. It's going to stop after that line, and it's never going to check our second function. We're not going to know if that one's working or not working. So what we want is some kind of way of automatically going through each of these test functions, not having to write them out manually at the bottom, but automatically finding out these test functions, running each of them in turn, and for each test function that gets run, printing out in the terminal, did that test pass or did that test fail? And even if a test fails, for it to carry on, keep on going, and keep on checking the rest of the tests, so we get a summary at the end of all of the good stuff and all of the bad stuff. So we could spend some time and write a Python program which looks inside this, tries to find all the functions that start with test underscore, runs them, catches the exceptions, etc., etc. We could spend some time doing that. Or we could use a tool which already does that for us, which is called PyTest, Python test. To make use of PyTest and to have it do its automatic magic for us, all we have to do, and I'm just going to simplify back to the situation where we had just one test for a moment. All we have to do is delete our explicit call to test add arrays, such that now this file only contains the definition of a function and doesn't explicitly call it. It's important that you delete the calling of the function. And now, if you run the pytest command on the terminal, inside the folder where our code is, just like that. So here it's given us a lot of information. So starting at the top up here, we ran pytest. It prints out a bunch of stuff which you can usually ignore. That's just information about the program running. It tells us it's found one item, which means one test. Then it goes ahead and runs the tests. So first it's running the tests that it found inside the file test underscore arrays.py. And for each test inside there, it's going to, along this line here, print a capital F in red if the test fails, or do a green dot if the test passes. And even if one fails, it will carry on and run the rest of the tests. At the end, it tells you at this point how many tests percentage has it finished. There's only one test, so after one test, it's done 100% of them. This red F is telling us that the one and only test in there failed. But then after it's finished all of those tests, it gives us explicit and verbose information about what's going on. So make this a little bit bigger here. Okay. So it tells us these are all the failures. It tells us the exact name of the test that failed. So this is the test that failed. It prints the full text of the code of that test with an arrow pointing at the line at which it failed. And then, and this is one of the really nice things about PyTest, it prints out the two things that you're comparing. It's saying you were asserting that output and expect were the same. Therefore, you were asserting that 579 and 57999 were the same. And furthermore, at index 2, you're saying that 9 and 99 are the same, but they're not. And so it's immediately giving us a lot of information about why the test is failing, which we can use to go back to our code over here and work out what's going on. Based on that, we can say, oh, okay, we made a mistake there. That should just be a 9. We run our PyTest again. And in the situation where it passes, it stays nice and quiet. We get a single green dot. We get a nice green banner printed at the end. It says one test passed in 0.04 seconds. So have a go at that yourself. All you should have to do in your code is delete the explicit call to test add arrays. So make sure you delete that line of code. So you've just got one function definition and the import in your file. Save it and run PyTest on the command line. Try breaking it and seeing what gets printed out then. Then what I want you to do is to go to the arrays file and make a second function called subtract arrays, which does exactly the same thing as this, but it has a subtract here, and write a test for your subtract arrays function as well. So then you'd have two tests here, one which is test add arrays, and one which is test subtract arrays. Oliver's asking, what's the benefit of using PyTest rather than a try except block inside test arrays? So the benefit of using PyTest is primarily, and one of the nicest things about it, is that it gives you this explicit verbose output. This stuff down here that's telling you about exactly what wasn't matching is being provided to us by PyTest. What PyTest has done is actually replaced assert with its own special assert, which is able to extract this information. If it was a normal try except statement, we would have to do all that work manually, so PyTest is providing that work for us. It also allows us to have multiple files which start with test underscore, with multiple functions in called test underscore, scattered all over our source code, and it will do the job of going off, finding them, and bringing them back, running them all in order, and summarizing the results of all of those tests. Joseph asks, do you have to use the assert statement to use PyTest? It doesn't absolutely require it. The way that PyTest decides whether a test has passed or failed is whether it has raised an exception which was uncaught or not. So the easiest and simplest way to raise an exception in Python is with an assert statement and with something which is either true or false. That is what PyTest generally expects, and it will be able to interpret it correctly. But we could do something like if they are not equal, raise value error. That would work fine, but then PyTest wouldn't understand how it failed. It would just see there was a value error raised, therefore your test failed. It wouldn't be able to give you the extra information that comes out at the end. So I do very much encourage assert statements when you're using PyTest. I'm just going to do the exercise that I've asked you to do by making a subtract arrays function. So if you're still working on it, feel free to follow along. So I see some questions in chat about PyTest doing nothing when you run it. So one of the reasons we ask you to use Anaconda for these courses is because Anaconda comes with PyTest installed by default. As Oliver says, if you don't have PyTest installed, you can install it with pip install PyTest, but you should all have it there already. If it ran the first time and then not running after, then it's not that you don't have it installed, it's that it's doing something strange. Does it return you back to the prompt, or does it just hang there for ages and not return you back so you can carry on typing? So it hangs. So the first thing to check when you're running PyTest is because it's going off trying to search for all of the files, the thing to check is that make sure you're inside the best practices folder. Otherwise, it's going to be going off searching your whole computer for all of the different potential files which could contain tests. That's one of the reasons why we encourage you to make the best practices folder so that everything is inside there, so that PyTest is only looking at the stuff that's local. So check that first, and that might be why it's hanging for a while. In the meantime, I have implemented subtract arrays. I've updated the documentation. I think I've updated it correctly. I've added a new example, and it has a subtract sign there. In my test arrays, I've now got a test subtract arrays function, which is using the same A and B. And as it happens, the expectation is that they should all be -3. We then call subtract arrays rather than add arrays. So now if we run PyTest, we should get 2 passing tests. I have to import subtract arrays. We should get 2 passing tests. There we go. So it's telling us inside test arrays.py, there's 1 test, 2 tests. They've both passed in a short amount of time. Because these single dots here aren't very explanatory, you don't know which test is being run at the moment, what I like to do is run PyTest in verbose mode, which you do by passing -v at the end of it. So if we run that, it'll print out a little bit more information. It prints out more at the top here, which you can continue to ignore. But it tells us this file, this function has passed, so it writes out the word in full. This file, this function has passed. And you see that after the first one, it's half done. After the second one, it was completely done. I almost always run with -v because I find it makes things look a little bit better. So the value in having done it this way is that we've managed to automate what's going on. We've got 2 test functions which are going to stay there forever, which are always going to be testing that our code is working correctly. And anytime we make any change to our code, we can always run PyTest. The value in using a tool like PyTest is that it automates some of the really tedious stuff about testing, because the only way you're realistically going to get around to writing tests for your code, let's be honest, is that if it's easy to do. If it's hard work, you're not going to bother. So you want to find tools which make your life easier, and PyTest, I feel, for Python at least, is one of the best. Other programming languages also have their own test frameworks which work in similar ways. PyTest is definitely the best one to use for Python. So one of the things we want to be able to do is to write multiple tests. So I'm going to move the subtract arrays one down a little bit, and we'll come back to that one in future exercises. I'm just moving it out of the way visually. And I'm going to write a second test here, which I'm going to call test add arrays 1 and test add arrays 2. Test add array 2, we're going to test something different. We've tested adding positive numbers together. Let's see what happens if we test adding negative numbers, because when you're writing code, it's very easy for positive numbers to work and negative numbers to not work. We expect -1 and minus that to equal -5, -5 and -3 to equal -8, and that to equal -3. So we've got one test, two tests, and a third one down here. We expect these both to pass. We run pytest-v, thinks about it, and it tells us they've all passed. Now that's all good and all, but what if we want to write a third test? We're copying and pasting code, we're repeating ourselves. It's easy to make mistakes when you're copying and pasting stuff. So what we want is a way for us to simplify down what we actually mean and get to the point a little bit quicker. Now looking at these functions here, what's actually going on inside there? The important part is test add arrays is a test function which has an output which is run on A and B. If this was a normal function we were writing, we'd passed A, B, and expect in as arguments, and we do assert output is equal to expect. And then we'd call this function multiple times, passing in different A, Bs, and expects. We factored out our common code, and we're just calling it with different inputs. We call it multiple times and check for each set of arguments that everything's working correct. So this is the core logic of the test. And so you can think about the test being split into two parts. There's the logic of the test, which is this bit, and there's the test data, which we actually want to check each time going over. And PyTest provides us with a way of splitting those things so that we can describe the logic in one place and the data that's being tested in another, and then combine them together automatically without having to repeat ourselves. And you do that by using a feature from PyTest. And because we're going to use a feature from the PyTest library now, we need to import PyTest. And what we're going to do, we're going to decorate this function with a Python decorator. And we're going to mark it as being parameterized. Parametrizer. I can never spell that word. And this is how we're going to call this function multiple times with different arguments. Because by default all these other functions took no arguments, PyTest was able to call them without having to worry about what the arguments should be. But this function here is expecting arguments, so we need to tell PyTest what those arguments should be. And we do that using this parameterize decorator. Now the parameterize decorator is a function. It takes two arguments. The first argument are the names of the arguments that are being passed in, or the names of the parameters that are being passed here. A, B, and expect. The second argument are the values of those arguments. I'm going to split it over multiple lines. Each argument inside this set of arguments inside this argument list should be a tuple with A, B, expect 1, 2, 3 things. And so the things we're going to pass in are A, B, and expect from our example up here. So A is going to be 1, 2, 3. B is going to be 4, 5, 6. And expect is going to be 5, 7, and 9. We can now pass in a second tuple of a list of arguments. And you see why I've done it over multiple lines here, because this can get a little bit verbose. I'm just copying and pasting the examples from before. And at this point, we've managed to reproduce all of those 15 lines of code in only 6 or so lines of code. It's having exactly the same functionality. This means we can delete our duplicated functions, and we've now got our test in a simplified format. We have the logic of the test, and we have the inputs to the test, where this tells us that it's going to pass in 3 arguments. We give the 3 arguments, it runs it, then it gives these 3 arguments, and then it runs it. So this test will be run twice, once for this set of data, and once for this set of data. So if we now run that with pytest minus v, we should get 3 tests run. We've only got 2 functions, but we have 3 tests. And you can see that happening here because the function test add arrays has been run once with one set of data, which is labeled, and it's been run the same function a second time with another set of data. So do that yourself. Copy in the test add arrays parameterize function. Just copy and paste it from the notes if you want to. Add in another example to the parameterize for test add arrays. And then try doing the same thing to test subtract arrays. Do the same thing with pytest, etc. and the same arguments that we had here to subtract arrays, and make sure that's able to be parameterized as well. Spend a minute or so doing that, and then we'll move on to the next section. So question there from Oliver saying, can you remind me what the at modifier is called? So this is a decorator. So if you search the internet for Python decorator, then you will see how these things work. It's a very cool feature of Python, which I'm hoping to write a course in the future to cover how they work. But at their core, what this bit of syntax does is it wraps the function that you put it in front of in a special way, and therefore can add information to it, it can check parameters, it can do various clever things. So there's lots and lots of different decorators you can use in Python, and PyTest provides a whole bunch of them. PyTest uses them quite liberally for things like marking tests. One thing you can do in PyTest, for example, is if you've got a bunch of tests, some of which are really, really slow to run, maybe they're downloading stuff from the internet and doing a full simulation run, you could mark them as being a slow test by using pytest.mark. And then when you run PyTest, you could say, for now, don't run the slow tests, just run the other tests to quickly check stuff. And then once you're finished for the day, you could do one run of your PyTest suite with the slow tests included, so that everything gets checked out as well. So it's a nice way of marking tests as being slow or needing to be run on Windows or not working at the moment, things like this. So far, we have been testing the inputs and outputs of functions. We've been saying this function has these things going into it, and this function has this stuff coming out of it. But in Python, there are more attributes of a function which are worth testing. So you've probably come across functions where you've called them, and instead of giving you a result back, they've instead errored. They've raised an error saying, you've tried to do something I don't understand. For example, if you do 1 divided by 0, you get a division by 0 error. Now that's not a mistake that it's returning to you. That is part of the definition of what the divide function does. It is designed so that if you give a 0 as the denominator, it will raise an exception. It's a promise that that's going to happen. You can rely on that happening. And so when you're writing code, if you've got a situation where you're using exceptions as a way of reporting to the user that they've done something wrong, and you're promising that if they do that same wrong thing again, they'll get that same error back, you should check that every time that wrong thing gets passed in, the error does indeed get returned. So let's do an example here. Let's go to our arrays.py and go to our add arrays function. So when we look at zip x and y, that is how we loop over 2 different lists at the same time. If we look at what happens if we call that by, for example, adding in an example which has, this has got 1 element in it, this has got 2 elements in it, what do we expect to get back from this function? Does anyone in chat want to offer what they think the return value of this function is going to be? Okay, 2 and nan. Now, as it happens, there's no such thing as nan in Python, so you'd have to do it in quotes or something. everyone else is saying he's going to get some kind of index error. Well, let's, for demonstration, guess that maybe it's going to return 5 plus 0. I mean, you probably will guess that's not going to happen, but maybe it's going to return 2, 5. Let's see what happens if we test that. We're fairly sure it's not, but finding out what's going to happen, best way sometimes is to run it. So what's happened here is expect we set to be 2, 5, but the output is returned is actually just the list 2. So yes, the test has failed, but the result of the function has succeeded fine. It has given us back an answer. And what it's done, it's truncated this list so it's the same length as this one, because that is what the zip function does. The zip function loops over 2 or more lists only as long as they all have elements. As soon as one of them runs out, they all stop. And so it's only going to give results as far as we've given inputs. And it does it silently, which is a matter of some contention in Python developer circles at the moment. So to stop someone making this mistake, and based on the variety of answers I got in the chat, it's clear that it's not a definite answer. The best thing to do is to be explicit for our users and tell them in this situation that they shouldn't do it. We should just say, no, that's not valid. And so the best way to do that, easiest way to do that, is to put at the beginning of your function a check. And we're going to check that the length of x is the same as the length of y. But if it's not, then we are going to raise a value error. We cover exceptions in our intermediate Python course, which are linked in the course notes here. Otherwise, there's hopefully going to be a video of that up online quite soon. And we put inside here some kind of message, like both arrays must have the same length. It's wrapped around there, but it's all the same. So now, if we run our code, running the same tests, now instead of getting the assertion error failing, it is now failing to run the code at all. And you get a lot of information printed out. Firstly, that test failed, but the other one's passed. It tells us that when it was calling this code here, when it was inside our add arrays function, this value error was raised. And so the test failed, but not because of an assertion error that our test was getting the wrong result, but because our function failed entirely. But that's not a bad thing. We want our function to fail in this situation. It's a promise we're making. In this situation, we are telling people that if they pass in different length arrays, they will get a value error. Because we're promising that, well, we should add it to our documentation. I think it's exceptions. And we say something like, oh no, it's raises. It raises a value error if the lengths of the lists x and y are different. I'm just going to indent this in a slightly strange way, but there we go. So this is now part of our documentation because it will happen every time. It's in our code, so we're making sure it's happening every time. But because we're now promising it, we should write a test which checks that it's true. And so we need to add a test into our test suite which checks that that error is raised in that situation. Now the way that you can check for errors being raised is again a feature of PyTest. So we are going to write a function called def test add arrays error. Not the best name, but it will do. We're going to pass in two lists, a equals 1, 2, 3, b equals 4 and 5. And then we're going to call our function output equals add arrays a and b. If we run this, we're going to get this same error happening because, in fact, now we can remove our example from there. We're going to get the same error happening. It's just going to raise an exception. But we want to kind of invert the logic. We want the test to pass if and only if this does raise the exception that we expect. If it doesn't raise an exception, that means that our promise has been broken, and that means there's something wrong with our code. So we want to pass the test if there's an exception, we want to fail the test if there is not an exception. It sort of seems backwards, but remember that exceptions being raised are part of our interface promise that we're giving. The way that we do that with PyTest is we use a with statement, which lets us wrap a block of code with some kind of condition. And we use the PyTest library .raises. So we're saying this block is expecting something to be raised. The thing that we're expecting to be raised is value error. And then we indent that block so it's part of it. So this is saying this code here is okay if a value error is raised. But if this code runs without a value error being raised, then PyTest will fail this test. So let's check if that's worked. It has indeed. It's now run test add arrays error, and it says that it's passed. If we now change this test so that it successfully does it, because it's not going to raise an error in that situation, then in this case, because they are the same length and we're expecting a value error, it now fails with did not raise value error. So it gives us an explanatory detail of what's going on. But that is the test that we want to check. And that means we can mess around with our code, change stuff around, and as long as we're fulfilling our promise, the test will carry on working. So add a similar test into subtract arrays. So do the same thing into your code, copy this in from the notes. You can do the same thing in subtract arrays, and then add in a test for subtract arrays, which does the same thing with pytest.raises, and check that you get the test passing when they are different lengths. But if you make it so that they are the same length and so no value error is raised, that the test fails correctly, as you would expect. So you can see I've done the exercise on my screen now. I've added in the code to subtract arrays, and I've updated the documentation. It's now going to raise an error if they're different lengths. And I've added a test at the bottom here, which is checking that if they are not raising an error when the lists are different lengths, then it should fail the test. The test passes, so everything is looking good. So this is all working nicely. We've got some tests which are building up, which are continually checking more and more aspects of our code. One of the nice things that you can do when you're writing tests is to build up your test suite based on errors that you find. For example, if someone emails you and says, oh, I found a mistake in your code where if you pass in these particular arguments, it doesn't give the expected output. What you can do is you can say, okay, so they've told me that if they pass in these things and these things, then it should give this, but it doesn't. What I would do is I would add that line with the actual numbers in to my test suite. I would run my tests and they would fail because, like they said, they reported the bug and it didn't work. I would confirm it by running it myself. And then I would work on my code until it starts passing. So that is why these parameterized sections are really nice, because you can just keep on adding more and more examples to your code. So one thing that we mentioned earlier was that we were doing our documentation strings. And inside our documentation strings, we had examples. We had subtract arrays is this, and this is what the result's going to be. And I said one of the problems with that is they can get out of sync. They can start to not match the code properly if you're developing your code. And so what you want to do is to make sure that the documentation you're writing matches the reality. So using PyTest, there's a way you can do that, and you can tell it to search all of your doc strings for these examples sections, run the code, check it against the example, and make sure it's working correctly. And the way that you do that, and I'll just remind myself, is by passing as an argument, skip the --v, actually no, let's put it in, --doctest, because it's testing your documentation, and you want it to search in modules for documentation tests. If you run that, it is going to do the same normal checks, but it's also going to look in your modules for tests. And it's found one for add arrays, and it's found one for subtract arrays. So in this way, your documentation tests can be seamlessly included into your test suite, which is a really, really valuable thing to have. I mentioned earlier about documentation-driven development, about how you would, if you were wanting to be really keen, you could write your documentation entirely first, then go ahead and write your code to match it. There's a similar idea with testing called testing-driven development or test-driven development. That is where you write your tests first, which describe what the inputs and the outputs of your function should be. When you run your test suite at that point, your test fails. But then once you've finished writing the contents of your function, your test suite will then start passing. So you describe your interface first, which is important because it's the interface that your users deal with. So you're thinking about your users first and what they're going to be seeing, checking what the inputs and outputs are going to be, and then from that, working out what the code should be. So writing documentation and tests before code is a really good way of thinking about how to describe your interface to other people, as well as exactly how it should work before you go ahead and start writing code. And this leads me to one of the most important things I think that you can take away from today's session, and it's something that took me a long time to learn for myself, and that is the interaction between good code and testing. I have found through trial and error over many, many years that if my code is easily testable, it automatically becomes better code. By making my code so that I can call the functions independently, check what the outputs are, it encourages me to write short, well-defined functions which are easier to compose, less mistakes in them, and solve the problem in a more direct and efficient way. Likewise with documentation, if my code is easy to document, it's going to make the code better because it encourages me to write short functions which are easily explained to people. So by thinking about documentation and testing right up front, it makes it so that your code automatically gets better. It's like a superpower. It's amazing how well it works. Making your code testable makes it better code. And while writing tests does seem like it's slow at first, over time you will find that writing tests overall does save you time, even taking into account the time that it takes to write the tests. Because you get fewer mistakes, you spend less time swapping around thinking about what you should be doing, you get to the point more quickly, and you know that it works more directly. So writing your tests and documentation up front, or at least thinking about them, is going to make your code better, and it will eventually make your code development faster, and that's a really, really useful thing to have. One thing we don't cover in detail in this course is automated tests. So it would be nice if you ran your tests every time you made a change. And if you've got your code in Git, for example, on GitHub, then what you want to be able to do is to automatically run your tests every time a change is made to your source code, so that you know every time someone puts in some more code, it hasn't broken anything. And so this is called automated testing, or sometimes continuous integration. If you have any questions about this, do feel free to email us. We're happy to answer any questions on these things, and we're planning on putting together some courses covering how to do automated testing in the future. So there's one last technique that I want to show you that PyTest provides, and that is called fixtures. It's a way of providing input data to your tests in a nice, concise way. So we saw before that we can split our tests into two logical parts. There's the data to be tested, which we were providing with the parameterize, for example, or sometimes inside the test. And then there was the actual code that performs the test. That's like the assert or the PyTest raises bit. And so in that situation, that worked well because we had one code example and we had multiple examples of data that we wanted to pass to the same bit of code. But sometimes it's the other way around. Sometimes you have one piece of data which you want to test in lots of different ways. For example, you've got one corpus of biomolecular molecules that you want to run different parts of your code base over to check that they all behave well with that bit of data. And sometimes that data can be quite large compared to anyway a list. Maybe that piece of data takes half a second to assemble or to load from a file or to download from the internet. And you don't want to have to download that bit of data every time you run a bit of test against it. You want to be able to download it once and run your test against that once downloaded piece of data. And this is a very common situation you have. Maybe you've got a database you want to create, fill with some dummy data, and then run your code against. Having something which provides that database statically for all your tests is really, really valuable. So I'm going to trim down my tests now a little bit in this file here, just to make things look a little bit clearer. And I'm going to do it just by copying and pasting, just to demonstrate a different point. So we're back to the situation now where we've got one for test add arrays, one for subtract arrays, and we haven't got our parameterized fixtures anymore. Otherwise it all gets a little bit messy. So what we can do, we see here that both these tests have got the same set of data. Now, it's clear that these data are quite small, but it might be that this was actually representing a heavier set of data. So we want to be able to provide A and B to both of our tests in a nice, consistent way. And A and B are these two lists. And so let's write a function which return those two lists. So here we've got, let's get rid of that, a function called pair of lists, which returns our A and our B. So that means we should be able to use pair of lists in this test and in this list test. Now we could do that by calling it inside those two functions, but PyTest provides a way of automatically providing that data to those tests. And also it provides a way of each test only having to get the data from the central store rather than each test recalling that function, therefore recomputing that data, and that might take some time. So to do that, we label our function providing our data as being a fixture. It is a fixture of data. It's a bit of terminology that's relatively PyTest specific, but it does sometimes crop up in other contexts. A fixture is a fixed set of data which is going to be used by all of your tests. Once you've described this function, you can then pass it in a slightly strange way, the name of the function as an argument to your tests. And now PyTest is going to automatically plumb this all together so that inside here we get access to A being pair of lists 0 and B being pair of lists 1. So this is going to go into here and therefore into A, and this 4, 5, 6 is going to go into here and therefore B. So now we're not having to define our data inside our tests, it's automatically getting passed through. That means we can run our test, it thinks about it, and we get, well, we've still got our Doctests. Let's clear that out so that we don't see stuff getting in the way. Run our test, and we see that our two tests have run, but we've only had to define our data once. Obviously, this is a dummy example. In real life, you'd have more complicated data sets going into this thing. To give a slightly more detailed example, I'm going to make a new file, which I'm going to call books.py. I'm just going to try and get this done before the end of the session. And a second file called testbooks.py. Books.py is a function which takes a text of a book and it counts all of the words inside there. And if you give it a second argument, it counts how many of that word there are inside there. So this is the sort of thing we want to be able to test on whole books. So let's have a look at our code to run the test. Again, I'm just going to copy and paste this. So what we have here is, I'm going to indent this, that's all one function call. We're going to have a function called test word counts, which is going to download this book here. It's going to read it into this text string here, and it's going to pass that whole book to the word count function, which is going to count how many instances of the word hat there are. And we're hoping that it's 33 because this is a test I did earlier. We can run this with pytest testbooks.py, and when we run it, it thinks about it for a moment and then comes back to the result. It thinks about it for quite a while. I'm going to change the screen. And that's because it's actually going away, downloading this file and unzipping it, basically. It's going and extracting it. So it takes several seconds to do, which is quite a long time for your test suite. You want test suites to be fast and pithy and to the point. So what we can do, if we wanted to run our test here, instead of just looking for the word hat, we wanted to look for all sorts of different word counts. Different things, the word hat, freedom, electricity, testing, Prince, internet, Russia, and Pierre. And we want to check all of them word and count, and we want to check that the count of word equals count. Now, if you can guess what book this is just from those list of things, feel free to post it in the chat. There's a prize. Well, it's not really. Let's pretend there's a prize for the first person who gets it right. You should have all the information you need there, along with the fact that it's a very long book. So now if you run this, in fact, I won't even wait for it to finish because it's going to take ages to run, because every single import PyTest. Every single example that gets run is it's going to re-download the file, and it's going to do that same thing over and over and over again. Every single time, for every word it's checking, it's downloading the file, checking it, then downloading the file, and it's checking it. And so this is going to take 30 seconds or something, which I don't want to wait for, so I'm going to cancel it. So what we can do, we can tell it that it should just get this book as a fixture and just do it once. So I'm going to turn that into a fixture. It's the same thing. It gets the book, it downloads it, and it returns it. And then in here, we are going to use that fixture. And we've turned the body of our test from all of that complicated stuff into something short and pithy, which says, count the number of word in long book and check that it's count. And all the details that go into that are provided A, by the parameterization, and B, by this fixture. So now when we run this, rather than it taking 30, 40 seconds, it should only take 2 or 3 seconds. It's downloading it once for the first test. That one takes a while to finish. But after that first test, the rest of them should be quite quick. But they're not just yet because it's still downloading it once for every test. Because there's one more thing we need to do, and that's we need to tell it that it should do it only once for the whole session. So if we now run this, it thinks about it, finds the tests. For the first test, it downloads the file, takes a few seconds to download the thing for the first test, and the rest just ping on through. And so the whole total time isn't 30 or so seconds, it's only about 5 seconds. So what fixtures provide is a way of only doing the complicated hard stuff once for all your tests, which means that your tests only take a short amount of time. And with that, we are done. So what we've covered today is documentation, making sure your users understand how to use your code, licensing, making sure they can use your code, and testing, making sure your code does what you promise it does. And for me, those are the big main 3 pillars of software engineering that we don't cover in other courses. The other pillar which you might consider to be very core, and I do consider to be core, is version control. Also, other things you might like to look into next are automated testing. We're hoping to have a course on that in the future. Code quality checks, that's automatically checking that your code looks nice and is formatted and all this kind of thing. And also packaging your code so that it can be used by other people nice and easily. Thank you very much for attending today, and I hope to see you all in a course in the future. Goodbye.